Why did this engine blow cost Greg Biffle everything? On the surface, that's a simple question with a simple answer. An engine failed, the aircraft crashed, and 3 people died. But the real answer is far more complex and far more troubling. Because Greg Biffle didn't just lose his life in this accident, he lost it in a situation that, under different circumstances, should have been completely survivable. Twin engine aircraft are specifically designed to fly safely on one engine. Pilots train for engine failures repeatedly. The Cessna Citation has decades of proven single engine capability. So, why did this particular engine failure on this particular flight cost everything? Welcome back to the channel. Today we're examining the Greg Biffle Citation disaster from a different angle, looking not just at what happened, but at why a survivable emergency became an unsurvivable catastrophe, and what that tells us about the risks hiding in plain sight in private aviation. Greg Biffle was no stranger to risk. As a NASCAR Cup Series driver, he spent decades operating at the absolute edge of control, piloting race cars at speeds exceeding 200 miles per hour, inches from other vehicles, with split-second decisions determining the difference between victory and disaster. He understood mechanical failure. He'd experienced engine blows on the racetrack, watched engines literally explode while running at maximum RPM. But on the racetrack, when an engine blows, you lose speed, you coast to a stop, maybe you create some drama and some smoke, but you walk away. The safety systems built into NASCAR, the safer barriers, the roll cages, the 5-point harnesses, the hands devices, all of it is designed to ensure that mechanical failures don't cost lives. Biffle had transitioned that same approach to risk management into aviation. He'd invested heavily in his pilot training, earning multiple ratings, including a multi-engine rating. He'd purchased a Cessna Citation II, a serious aircraft requiring serious training and serious respect. By all accounts, he was passionate about aviation, committed to doing it right, working toward the goal of being able to fly the Citation himself as pilot in command. He understood that aviation, like racing, demands preparation, demands respect for the machine, demands recognition of the risks involved. But here's what makes this accident so tragic and so instructive. All that preparation, all that training, all that respect for the risks, it wasn't enough, because the risk that ultimately killed Greg Biffle wasn't the one he was preparing for. It was hiding in the margins, in the gaps between what's legal and what's safe, between what's technically sufficient and what's actually adequate, between what the regulations require and what reality demands. And when the engine blew on that January morning, those hidden risks converged in a way that cost him everything. Let's start with the engine itself, because understanding what happens when a jet engine fails catastrophically is critical to understanding this accident. The Cessna Citation II is powered by 2 Pratt & Whitney JT15D turbofan engines. These are proven, reliable engines with thousands of examples in service worldwide. Under normal operations, each engine produces approximately 2,500 pounds of thrust. The 2 engines together provide enough power to climb at over 2,000 feet per minute, to cruise at 41,000 feet, to fly over 1,000 nautical miles. But jet engines are also incredibly complex machines operating under extreme conditions. Inside the combustion section, temperatures exceed 2,000 degrees Fahrenheit. Turbine blades are spinning at tens of thousands of RPM. Compressor stages are pressurizing incoming air to ratios of 10-to-1 or higher. Fuel is being injected and ignited in precisely controlled amounts. Everything has to work in perfect harmony, with tolerances measured in thousandths of an inch for the engine to function. When something goes wrong, when something disrupts that harmony, the results can be catastrophic. And one of the most destructive things that can happen to a jet engine is foreign object ingestion. When something solid enters the engine intake, something that's not supposed to be there, it gets immediately struck by the fan blades spinning at tremendous velocity. Those fan blades, despite being made of titanium or hardened steel alloys, can bend, crack, or completely shatter when they strike a solid object at high speed. The destruction doesn't stop there. Pieces of destroyed fan blades become projectiles themselves, traveling forward and backward through the engine. They strike compressor blades, destroying them. They damage the combustion liner. They strike turbine blades. Within seconds, a perfectly functioning engine becomes a destroyed piece of scrap metal. RPM drops to 0. Thrust goes to 0. Oil pressure drops. Exhaust. Gas temperature spikes as burning fuel passes through without being properly combusted. Every warning light and alarm associated with that engine activates simultaneously. This is not a gradual failure. This is not the engine slowly losing power over minutes, giving the crew time to diagnose and respond. This is instantaneous, catastrophic, complete engine destruction in a matter of seconds. And based on the physical evidence from the Biffle accident, this appears to be exactly what happened to the right-hand engine, the number 2 engine, shortly after takeoff. Post-crash photographs examined by multiple aviation analysts show clear and significant damage to the fan blades of the right-hand engine. The blades are bent, twisted, some appear to be missing entirely. This is the signature of foreign object damage, FOD in aviation terminology. It's exactly what you would see if something solid, something substantial, had been ingested into the engine while it was running at high power. We also know from those same photographs that the right-hand forward baggage compartment door is missing from the wreckage. Now, the NTSB has not yet officially confirmed whether that door was torn off during the crash impact or whether it separated in flight. But the combination of a missing baggage door and a destroyed right-hand engine is not coincidental. It's a pattern we've seen before, and it points to a very specific failure sequence. The forward baggage compartments on the Citation II are located in the nose of the aircraft ahead of and below the cockpit. There's one compartment on each side, left and right, each with its own access door. These doors are secured by mechanical latches. You open the door, load your baggage, close the door, and manually secure the latches by moving handles into the locked position. There's nothing complicated about it. It's a simple mechanical latch, the kind that's been used on aircraft for decades. But here's the critical flaw. On these older Citation models, there is no electronic monitoring of these doors. There's no sensor that detects whether the door is closed. There's no sensor that detects whether the latches are secured. There's no warning light in the cockpit. There's no master caution annunciation. There's absolutely nothing that tells the pilots whether these doors are properly secured or not. The only way to know is to physically look at them and verify that the latches are engaged. This is what aviation human factors experts call a single point failure mode with no backup. The entire system depends on one person remembering to check those latches and securing them properly. If that person forgets, if they're distracted, if they think someone else already did it, if the latches appear to be secure but aren't fully engaged, there's no safety net. The first indication the crew will have of a problem is when they're already airborne and the door blows open. And when that door blows open at 100 and 50 knots in a climb, the results are immediate and dramatic. The pressure differential between the inside and outside of the compartment, combined with the tremendous airflow, creates a suction effect. Items inside the compartment, suitcases, bags, loose articles, anything not tied down, are immediately sucked out. And because of the location of that baggage door, directly ahead of and slightly inboard of the right-hand engine intake, there's a very high probability that at least some of those items will go directly into the engine. This exact scenario has happened before. In 2024, a Citation II departing Barranquilla, Colombia, experienced an opening of the right-hand baggage door shortly after takeoff. Items were ingested into the number 2 engine. The engine sustained catastrophic damage and failed completely. The crew declared an emergency and returned to land safely on one engine. Everyone survived. In 2007, another Citation experienced a baggage door opening shortly after takeoff. In this case, the crew became distracted by the noise, the chaos, the visual disruption. They lost focus on flying the aircraft. Airspeed decayed. The aircraft stalled at low altitude. There was insufficient altitude to recover. Everyone died. So we have two precedents, same initiating event, two completely different outcomes. One crew survived, one crew didn't. The difference wasn't the mechanical failure. The difference was everything else. The margins, the crew capability, the decision-making, the altitude, the time available to respond. And this is where we start to understand why this engine blow cost Greg Biffle everything. The flight departed Statesville Regional Airport at approximately 10:05 local time on a January morning. Weather conditions were marginal VFR. Ceilings were reported at 1,200 feet broken, visibility 5 miles in light drizzle. Temperature and dew point were close together, creating moisture and low-hanging clouds. These are legal conditions for visual flight operations, but they're not comfortable conditions. You're operating right at the edge between VFR and IMC. One wrong turn, one slight descent, and you're in the clouds whether you intended to be or not. The Citation lifted off from runway 10 and began what appeared to be a normal initial climb. But somewhere in those first couple of minutes, the baggage door apparently opened. Items were ingested into the right-hand engine. The engine destroyed itself. And suddenly, what had been a routine departure became a life or death emergency. Now, let's be very clear about something. A single engine failure on a twin-engine jet should not be a life or death emergency. It should be a serious situation requiring immediate action and proper procedures, but it should be manageable. The aircraft is specifically designed and certificated to fly on one engine. Pilots are specifically trained to handle this exact scenario. There are written checklists, memory items, established procedures. This is a known emergency with known responses. But all of that assumes certain things. It assumes you have adequate altitude to work the problem. It assumes you have adequate time before you must be back on the ground. It assumes you have two competent pilots who can divide the workload, one flying the aircraft while the other manages systems and checklists. It assumes the pilots are properly trained, current, and proficient. It assumes they make correct decisions under stress. When all those assumptions hold true, engine failures are survivable. When they don't, they're not. Let's talk about altitude, because altitude in aviation is everything. Altitude is time. Altitude is options. Altitude is safety. When you're at 10,000 feet and you lose an engine, you have perhaps 15 to 20 minutes before you must be on a runway. That's enough time to run all the checklists, coordinate with ATC, set up a proper approach, brief the landing, maybe even troubleshoot to see if you can restart the engine. You have time to think, time to plan, time to execute properly. When you're at 2,000 feet and you lose an engine, you have perhaps 3 to 5 minutes. That's barely enough time to turn around, line up with a runway, run the immediate action items, and get configured to land. There's no time for troubleshooting. There's no time for discussion and debate. There's barely time to execute the basics. And if anything goes wrong, if you make any mistake, if you misjudge your altitude or your distance, you're out of options. The limited ADS-B tracking data we have suggests the Biffle flight climbed to approximately 2,000 feet before leveling off and beginning to maneuver back toward the airport. 2,000 feet, that's not much altitude. That's maybe 2 to 3 minutes of time before you must be on a runway. And if the engine failure occurred even lower, if it happened at 1,500 feet or 1,000 feet, the available time would have been even less. Compare that to the Barranquilla incident where the crew had climbed to several thousand feet before the emergency occurred, where they were operating from a major international airport with long runways and full ATC services, where the weather was good and visibility was unlimited. They had margins, they had time, they had altitude, they had options. The Biffle flight had none of those things. Now let's talk about crew capability, because this is where the hidden risks really start to emerge. We know there were 3 people on board. All 3 were certificated pilots, but only one, Dennis Dutton, held a citation type rating. Only Dennis was legally qualified to act as pilot in command of this specific aircraft. Dennis was 67 years old, a retired Delta Airlines captain with over 30 years of professional flying experience. By every measure, he was highly qualified and highly competent. The other 2 occupants were Dennis's son, Jack, age 21, a college junior in Auburn's professional flight program, and Greg Biffle himself, age 54, NASCAR driver and aircraft owner. Jack held a private pilot certificate for single-engine land aircraft with a recent instrument rating. According to FAA records, he did not hold a multi-engine rating. That's significant because it means he was not legally qualified to serve as a required crew member on any multi-engine aircraft, let alone a jet. Greg Biffle held a multi-engine rating. Under Part 91 regulations governing private operations, he could legally serve as second in command if he met certain familiarization requirements, knowledge of aircraft systems, emergency procedures, a certain number of takeoffs and landings. But we don't know his actual proficiency level. We don't know how much citation time he had. We don't know if he'd completed formal training or just accumulated hours. There's a huge difference between being technically legal and being truly proficient. This matters because of how multi-crew operations are supposed to work. The fundamental design assumption for aircraft like the Citation is that you have 2 pilots, both competent, both trained, both capable of performing their respective duties. The pilot flying focuses on flying the aircraft, maintaining control, managing flight path, handling navigation. The pilot not flying, also called the pilot monitoring, manages systems, runs checklists, handles radio communications, monitors instruments, and calls out deviations. When an emergency occurs, this division of labor becomes even more critical. The pilot flying has to fly the aircraft with degraded performance, asymmetric thrust if an engine has failed, possibly an IMC or marginal weather, while maneuvering back to the airport. That requires 100% of their focus and attention. Meanwhile, the pilot not flying has to diagnose the problem, identify which engine has failed, run the engine failure checklist, which contains dozens of steps, shut down the failed engine properly, reconfigure aircraft systems, declare an emergency if in contact with ATC, set up and brief the approach. This only works if both pilots are competent. If the pilot not flying doesn't know the systems, doesn't know the checklists, doesn't know what to do, then the pilot flying is essentially alone. They're trying to do two jobs simultaneously, fly the aircraft and manage the emergency. At low altitude with minimal time, that's nearly impossible, even for a highly experienced pilot like Dennis Dutton. And this is where we get to the question the NTSB already knows the answer to, but hasn't publicly disclosed yet. Who was in that right seat? This aircraft had a cockpit voice recorder installed, left over from when it operated under Part 135 charter rules. That recorder captured everything, every word spoken, every switch click, every warning tone. The NTSB knows exactly who was sitting where and exactly what happened in that cockpit. If Jack Dutton was in the right seat, despite not having a multi-engine rating, then Dennis was essentially flying solo. Jack, despite being a smart kid passionate about aviation, would not have had the training or experience to help with citation systems and procedures. He'd never flown a multi-engine aircraft. He'd never experienced an engine failure. He wouldn't have known what to do beyond perhaps calling out airspeeds or altitudes. In an emergency requiring immediate, precise action, he would have been a passenger, not a crew member. If Greg Biffle was in the right seat, the question becomes one of proficiency. Was he truly capable of serving as an effective second in command in an emergency? Had he trained for engine failures? Did he know the checklist? Could he run them quickly and accurately under stress? Or was he still learning, still building proficiency, not yet ready to handle a real emergency? We don't know the answer yet, but we know this. In the airlines, both pilots are extensively trained, regularly checked, required to complete recurrent training every 6 months. Both pilots are fully capable of handling emergencies. In Part 91 operations, you can have one very experienced pilot and one person who barely meets regulatory minimums. That second person might be legally qualified, but functionally useless in an emergency. And that gap between legal and capable is where people die. There's another factor we need to discuss, and it's one that often doesn't get enough attention in accident analysis: task saturation and psychological stress. Even for highly experienced pilots, emergencies create stress that degrades performance. Your heart rate increases, adrenaline floods your system, your fine motor skills degrade, your cognitive processing slows, you develop tunnel vision, literally and figuratively, focusing on one aspect of the problem while losing an awareness of others. This is why training and procedures are so important. When you've practiced emergency procedures dozens or hundreds of times, when you've sat in a simulator and dealt with engine failures until they become almost routine, your trained responses can take over even when your cognitive function is degraded by stress. Muscle memory, procedural memory, these can carry you through when conscious thought is overwhelmed. But if you haven't trained extensively, if you're dealing with an emergency you've never actually experienced before, if you're in a high workload situation at low altitude with minimal time, the stress can be overwhelming. And this is where mistakes happen. You forget a step in the checklist. You misidentify which engine has failed and shut down the wrong one. You fixate on troubleshooting the problem and stop monitoring airspeed and altitude. You misjudge your position and descend too early. Any of these errors in a low altitude emergency with no margin for error can be fatal. Now let's talk about decision making, because in the immediate aftermath of an engine failure on takeoff, you face critical decisions that will determine whether you survive. The first decision is whether to continue straight ahead and climb away or to immediately turn back toward the airport. Both options have risks. If you continue straight ahead, you're flying away from the airport. You'll need to climb, gain some altitude and some breathing room, then turn around and come back. This gives you more time to work the problem, more altitude to work with, less aggressive maneuvering. But it also means you're getting farther from the runway, and if your single engine performance is marginal, you might not be able to climb effectively. You might just be delaying the inevitable while using up distance and energy you'll need to get back. If you turn back immediately, you're keeping the airport close. You might be able to get back to a runway within a minute or two, but you're maneuvering at low altitude and low airspeed, which dramatically increases the risk of a stall or loss of control. You're turning with asymmetric thrust, which makes the aircraft want to roll and yaw. You're descending while turning, which increases load factor and stall speed. It's a high-risk maneuver. The standard guidance for light twins piston engine aircraft is that below about 400 to 500 feet, you should not attempt to turn back, land straight ahead, or with only minimal maneuvering. You don't have the altitude. But jets have better performance than light piston twins. They climb faster, they have more excess power, their single engine capabilities better. A turn back that would be suicidal in a light twin might be survivable in a jet like the Citation. But that decision requires accurate assessment of your situation. You need to know your altitude precisely. You need to know your single engine performance at your current weight and temperature. You need to know the wind direction and how it affects your ground track. You need to know where the airport is, which runway you can reach, what the approach path looks like. All of this has to be processed and decided within seconds while dealing with the immediate demands of flying an aircraft with a failed engine. From the limited tracking data, it appears the Biffle flight made a decision to return. They climbed to about 2,000 feet, leveled off, began maneuvering back toward the airport. They were attempting to set up for runway 28, the opposite direction from their departure. That suggests they made a plan and were executing it. So why didn't it work? The aircraft impacted terrain approximately 1,800 feet short of the runway threshold. 1,800 feet. They were close. So close. If they'd had just a few hundred more feet of altitude, if they'd been a few knots faster, if they'd been on a slightly different approach angle, they would have made it. But they didn't. They came up short, and that's all that matters. The question is why? Why were they low? Was it a misjudgment of altitude or descent rate? When you're flying a visual approach in marginal weather with low clouds and reduced visibility, it's very easy to misjudge your height above the ground. You don't have clear visual references. You can't see the horizon clearly. Your depth perception is compromised. You might think you're at 800 feet when you're really at 500. You might think you're a mile from the runway when you're really at 2 miles. Was it excessive descent rate? When you're flying on one engine, especially if you're flying slower than normal to maintain better control, your descent rate on approach will be higher than normal. You don't have as much excess power to arrest the descent. If you misjudge this, if you let yourself get on a too steep approach path, you might not be able to shallow it out. You might be committed to a descent rate that's going to put you short of the runway. Was it loss of additional power? This is speculation, but it's worth considering. If the right engine was destroyed by FOD, could pieces of that engine have damaged other systems? Could debris have struck the left engine intake? Could hydraulic lines have been severed, reducing controllability? Could the crew have inadvertently shut down the good engine while trying to secure the failed one? This happens more often than you'd think. In high-stress situations, pilots have been known to shut down the wrong engine, leaving them with no power at all. Was it an aerodynamic stall? This is one of the most common factors in accidents following engine failures. The crew, desperate to make the runway, pulls back on the controls trying to stretch the glide. Airspeed decays, angle of attack increases, the aircraft approaches stall speed, and especially in a turn where stall speed is higher due to increased load factor, the aircraft stalls. At low altitude, there's no time to recover. The aircraft enters an accelerated descent, and it's over. We don't know which of these factors or which combination caused the aircraft to come up short. The NTSB investigation will determine that. The CVR will tell them what the crew was dealing with, what they were saying, what warnings were sounding. The flight data recorder, if this aircraft had one, or the radar and ADS-B tracking, if not, will tell them the flight path, the speeds, the altitudes. The wreckage examination will tell them the positions of controls, the configuration of flaps and gear, the condition of both engines. But we can already identify the contributing factors, the reasons why this engine blow cost everything instead of being a survivable emergency: inadequate altitude at the time of the emergency, marginal weather reducing visibility and visual references, possible inadequate crew capability with one pilot potentially flying alone, high workload and stress-degrading decision-making, minimal time to respond and execute procedures, any misjudgment or error being immediately fatal due to lack of margins. This is the harsh reality Greg Biffle faced that morning. He was in an aircraft capable of flying on one engine. He was with a pilot fully capable of handling an engine failure. He'd invested in training and preparation, but none of that was enough because the margins that should have been there weren't. The altitude wasn't enough. The time wasn't enough. The crew capability may not have been enough. The weather didn't provide enough visual reference. And when you're operating with zero margins, when there's no buffer for any error or any misjudgment, a survivable emergency becomes unsurvivable. In NASCAR, Greg Biffle understood the concept of margins. You don't race with bald tires, even though technically they might last the race. You don't run with minimum fuel, even though mathematically you have enough. You don't push the engine to the absolute limit every lap, even though technically it can handle it. You build in margins, buffers, safety factors, because when something unexpected happens, when a tire loses pressure or another car makes contact or debris appears on the track, those margins are what save you. The same principle applies in aviation, maybe even more so. You don't fly in marginal weather when you could wait for better conditions. You don't operate with minimally qualified crew when you could have experienced professionals. You don't depart with questionable maintenance items when you could have them properly addressed. You don't accept single point failure modes when you could have redundant systems. You build margins into everything you do. But Part 91 operations, private flying often operates with minimal margins. The regulations allow it. You can fly VFR in marginal conditions. You can have minimally qualified second-in-command pilots. You can defer maintenance that airlines would never accept. You can make decisions based on convenience rather than optimal safety. And 99% of the time, you get away with it. The flight goes fine. Nothing bad happens. The thin margins don't matter until they do, until that one time when something unexpected happens, when an engine blows or a door opens or weather deteriorates faster than forecast. And suddenly those thin margins that never mattered before are the difference between walking away and not coming home. That's what happened to Greg Biffle. The margins that should have been there, that could have been there, that in a different operation would have been there, they weren't. And when the engine blew, those missing margins cost everything. The preliminary report will be released soon. We'll learn more details. We'll find out who was in which seat. We'll learn what the CVR captured. We'll learn whether the baggage door was found and what condition it was in. We'll learn the exact sequence of events. But the fundamental lesson is already clear, and it's one that applies far beyond this specific accident. Margins matter. In racing, in aviation, in any high-risk endeavor, margins are what keep you alive when things go wrong. Legal minimums are not safety targets. Technical compliance with regulations is not the same as actual safety. And when you operate at the edge, when you accept thin margins, when you tolerate single-point failures, you're gambling that nothing will go wrong. Most of the time, you win that gamble, but when you lose everything.